Here is a problem of variable mass system. A chain AB of length L is located in a smooth horizontal tube so that its fraction of length h hangs freely and touches the surface of the table with its end B. At a certain moment, the end A of the chain is set free. With what velocity will this end of the chain slip out of the tube? So we are, let's imagine it like this, a table surface, and we got a chain just placed such a way one end B is touching the floor, the other end A is over here. I'm told this height is say h. Now let us consider some intermediate situation where we got some length x on the top, and of course the same h over here, and some length, like as we are neglecting the heaps formed as the bottom B has moved, so that now this length would be, we can write L minus h minus x, right? So at this situation, let us say this is at t equal to 0. This is at some t equal to t. At this situation, let us consider the forces that are there. Say here is now let's consider the free body diagram for this part. Free body diagram for this part, let us say this part is accelerating to the right at A, then this part is accelerating down at A. Definitely they should have the same acceleration. So for this part in the free body diagram, we can show the tension force T, let us say, and it is accelerating to the right. So T is equal to lambda x is its mass, because x is the length, mass into acceleration. And for this vertical part, we can write the equation. For the vertical part, we have gravitational force, we have the tension T, and the gravitational force, because at the same point we are talking, hence we are showing the tension same as T, and the mg for this part, and this is having an acceleration here, so we can write mg minus t, where m can be written as lambda h is the mass into g minus t, that should become equal to lambda h here. So we can eliminate tension. So on eliminating the tension, we would have lambda hg minus lambda xa is equal to lambda ha. We can cancel this lambda on both sides. We would have hg minus hg equal to xa plus ha. So therefore we would arrive at acceleration as gh by h plus x. In the problem, we are asked about the velocity with which that chain will be sliding at the moment when this A totally come out of that tube, horizontal tube. Anyway, let us get the velocity expression as a function of x. So as to get that, you know that x is decreasing, as velocity is increasing. So we can write that acceleration, which is, again I'm putting a equal to gh by h plus x. So we can write a as minus v dv by dx equal to gh by h plus x. So we would have minus v dv equal to gh by h plus x dx. We can take integral on both sides. Initially it is released from rest, and let's say it has some speed v at the instant when that upper portion length is x. Initially the upper portion length was L minus h, and now it is x because we are bothered about integrating over x. So we would have on the left side minus v square by 2 equal to gh, and on the right side we would have a logarithm h plus x, but we have to put the limits. If I put this x as the upper limit, I would have h plus x divided by the lower limit. In the place of x, I have to put L minus h. So I would be having L in the denominator. So if I write velocity, we got it as minus v square by 2 and equal to gh logarithm. We have h plus x by L. So let us rearrange everything. So we would have what? V equal to root 2 gh ln L by h plus x. This would have. We are asked to give the velocity at the instant all the chain come out of the tube. That means x is going to be 0. Therefore, at x equal to 0, we get v equal to root 2 gh ln L by h. So that is the answer for this problem. Let's look into the next question. In the figure here, it is shown a rope is pulled up. So let us read the question. An external agent pulls a uniform rope of linear mass density lambda, and its length is given as L by holding its tip vertically upward with uniform velocity v. Rope is initially lying at rest on the floor. Neglecting the bending effect, find the force exerted by external agent as a function of length above the floor, and it is indicated as y. So in this example, as the rope is pulled up, let us consider some instant where we got, say, at some, this is the rope, say at t equal to t, let's say this is y. Now at t equal to t plus dt in a very small interval, you would see instead of y, the raised length would be y plus dy. And it is told we are maintaining a constant speed v. That means we can observe here as the agent who is pulling up with some force, the force is doing some work in increasing the length of that standing part through dy. You see that dy element is the increment in the length, but that element has some mass. That element has also picked up, which was at rest previously. Now it is having some speed v. So there is a kinetic energy increase in the system. Not only that, the dy increment is also showing an increment in the potential energy. So the increment in the kinetic and potential energies is accounted as work done by the forces. Let us, we can go with the idea of conserving the energy or we can go with the application of work energy theorem. As we know that work energy theorem, the elementary work done by all forces, PW, is equal to the elementary increment in the kinetic energy of the system. So now here, work done, say the force that we need to find the force. Let us say that force external agent applying is F. So uh, we can write the force to be doing some work. The displacement caused by the force is dy. So F dy, and dy is in the direction of the force applied. And gravitational force is doing work. So work done by gravitational force is, if we observe that you can just see that the element dy is here, dy was here first, was here, and now the dy you can treat it to be here. The remaining part is the same as usual in the previous case. So the dy element is raised through y, we can understand. A dy element was resting on the floor in a small interval dt. You got the dy at the top. I'm just considering an equivalence here because when the rope is pulled up, every element of the rope is moving up. Every element's potential energy is increased. Instead of finding for each and every element, it is just simple. Because the standing length y, as in the previous and this case, is the same, their potential energies are the same. The only difference is caused because of the dy, but the dy is raised to y. So you can write that work done by gravitational forces, lambda dy is the mass, into g, into it is raised through y, and you are indicating a negative sign here because gravity is down and dy is lifted up. So negative work done. F dy has done a positive work. Only these forces are there, and that is equal to change in kinetic energy of system. Change in kinetic energy of system is the previously and the present. The length y has got the same speed and same mass. So there is no change in kinetic energy in length y. The excess kinetic energy added to system is that is the kinetic energy of the element dy. Therefore, half mass of that element is lambda dy is the mass into, as we are pulling it up with a constant speed, we can write this. So if you observe the entire equation, you would have further f can be written as f minus lambda gy. As I'm removing dy on both sides, you would have lambda v square by 2. So that implies the force that you have to apply is equal to lambda gy plus lambda v square by 2. So this is the force required to pull that rope with a constant velocity v. And here, compared additional to the previous things, you got an additional sentence in the next page for the same problem. Also find the average power and maximum power delivered by the agent in pulling the entire rope. I got the force and I got that rope has velocity v in the direction of applied force. Therefore, instantaneous power is F into V, as F and V are in same direction. That can be written as lambda gy V plus lambda V cube by 2, it would become. So this is the power as a function of y. Everything is same constant, remaining all things. Just y will decide the power. So for P max, therefore, we are finding P max. Therefore, for P max, we can put the maximum value for y. The maximum value for y is the length L. So when you are completely bringing up all the rope to the vertical at that instant, you are delivering maximum power. This is the expression for maximum power, and you need to find the average power. I'm using this kind of symbol for average power. So as p is a function of y, I'll write integral p dy, integral dy. We are talking for lifting the rope because power delivered in pulling the entire rope is the question. So 0 to L. So let me put p as a function of y. We would have lambda gy v plus lambda v cube by 2 dy going from 0 to L. And integral dy is L. So children, we would have lambda gv, that is y square by 2. Y square by 2 gives me L square by 2 in the numerator, and lambda v cube by 2 into L divided by L. So finally we would arrive at average power lambda gv L by 2 plus lambda v cube. So this is the expression for the average power delivered by the agent in pulling the entire rope. So we did now the problem of the rope, pulling the rope. I have used the idea of conservation of energy or work energy theorem. Now let us go to the other part of the problem, other question. See, the question is continuing the same thing. Assume in the previous question the rope is replaced by the chain containing small sized large number of links, and external agent pulls the chain in infinite number of small steps, causes static, in such a way that within each step velocity remains constant and is v. Find force exerted, force required to pull the chain as a function of its standing length y. So you got chain here. You got now. So there is a bit of difference. You have a continuous mass carrying in the example of the rope, but when it comes to chain, the links are coupled. Now between these links, there will be the interaction forces that you would have to be considering when you're lifting this chain. So now to lift the chain, so that again you need to find the force, say as a function of y. So I'll use the force method here. So force, as I am pulling, as there is an increment, that is mass is adding to the system, there is a discouraging thrust to the additional external force. So we can write v relative dm by dt, which would be equal to mass into acceleration. But here, acceleration is 0. Not only this, you also got for this chain that is being pulled up, there is gravitational force, hence we can write minus mg, which is downward, the force is upward. So we can write that required force is mg plus v relative dm by dt. Now you have to estimate for m. M is the weight of this standing part of the chain, that is lambda into y into g, plus v relative is v dm by dt. Dm by dt stands for d by dt of lambda y, but dy by dt is again v. Therefore, the force that is required in this example is lambda gy plus lambda, we can write outside v dy by dt. Dy by dt is v. So we can write the force required is lambda gy plus lambda v into v. So lambda gy plus lambda v square. I want you to observe the difference in case of the rope and the chain. We got for rope the same thing we did for chain also. For chain, We did in both the cases, we found the force required to lift them so that their velocity speed remains kept constant. We got for rope lambda gy plus lambda v square by 2. But here we got the force lambda gy lambda v square, that is lambda v square by 2 plus another lambda v square by 2. Here if you estimate power in the case of rope, power is regarded as lambda gy v plus lambda v cube by 2. We can write the power in this case also lambda gy v plus lambda v cube by 2 plus another lambda v cube by 2. How do we account? We account this for the weight, I mean energy spent so as to bear the weight, and this for supporting the kinetic energy uh, for all elements, and so we added elements kinetic energy, that is. So here also similarly work done, I mean power delivered to overcome the gravitational pull, energy spent against it. This is for kinetic energy, and this would be some dissipated energy, heat energy, dissipated energy. Why the dissipated energy we are accounting? Because the chain has got links, and between the links you got some force, so that there is a scope of heat developed. So there is a difference when we are working with rope and the chain, as rope is a continuous mass distribution, not as like you got coupling as like chain. So the expressions for force required to lift the rope and the chain are coming out to be different. We are going to the next part. In this example, a chain of length L is held vertical and then released on a platform, which starts from rest at the same moment upwards with a constant acceleration A. Here you can see this platform, whichever is there, whichever is there, it is movable platform, and it is moving upward with some acceleration A. And the chain was initially at rest, the chain is held vertical. You are asked to determine the total force exerted on the platform by the chain as a function of time. Say at a t equal to 0, you got all the chain L, and this has started to accelerate up. But at t equal to some t, say now that length b, say that it is some y, this is accelerating. Now you got some heap of the chain sitting on this platform. So let's work out the problem relative to platform. Relative to platform. We can say that effective G is G plus A in this example, because you can see that as the platform is going up with respect to platform, you can write every element will be experiencing a pseudo force vertically downward along with mg. So like you can write any element you take of dm, it will have dmg as well as a pseudo force dm into A. So this is the pseudo force. So now we can instead represent that dm into g plus A, where that g plus A we were like you can pronounce it as g effective. So with respect to platform, when I'm working, you're asked to find the force exerted on the platform by the chain. So as the mass is added to the platform, you can write here force can be you got L minus y length of the chain is now on the platform at this instant. So lambda into L minus y is the mass that is there on the platform into G. This corresponds to the force of that chain already came onto the platform. But I have to take, instead of G here, G plus A, which is effective G. And as mass is added, the force on the platform due to the thrust of the added element would be V relative to the platform for every element into dm by dt. This is the force on platform by chain. So that F is equal to, once again, lambda into L minus y into G is nothing but here in this case G plus A, and we have V relative dm by dt. So this contributes. V relative is, you can use with respect to platform, as every element has fallen through some L minus y, we would have V square minus 0 square equal to 2 times acceleration. If for any element, it has now fallen through L minus y, because now y is standing length. So that V relative would come out to be root of 2g plus a into L minus y. And you can write that dm by dt part is lambda times dy by dt. So we would have it as lambda v square. So lambda L minus y g plus a plus lambda into 2 times g plus a L minus y. So we would arrive at 3 times lambda L minus y into g plus a. This would be the force. This would be the force. Now, for this L minus y, but L minus y is what? We can write half into g plus a into t square, because we are asked to give the force as a function of time. So we can put 3 lambda in the place of this. We can write that g plus a into t square into g plus a. So finally, therefore, force on platform would be 3 lambda by 2 g plus a whole square into t square. So that is the answer for the force due to the chain on the platform, which is accelerating up. Here is another question. A particle of mass m0 is projected vertically upwards with an initial velocity u. So you have now u is given as some g into tau, where tau is some positive constant is told, and mass of the particle keeps increasing, it seems. It's given the rule at which mass increases m equal to m naught e power t by tau because of vapor condensing onto the particle. Find time of ascent of the particle, maximum height reached by the particle. Neglect air resistance and buoyant force of the medium. So as the particle is going upward, it is experiencing a downward gravitational force. And as a mass is added to the particle, due to that added mass, there is a downward thrust on the particle. So we can write this equation: downward gravitational force and downward thrust V relative dm by dt mm, that should be the net force, and that should be equal to product of mass and acceleration. So we can divide. We can write minus of g plus v is at any point of time. I'm assuming v is the speed of the particle. So v by m dm by dt equal to a. Given that m is m naught e power t by tau, so if I differentiate dm by dt, it should be m naught e power t by tau by tau. Suppose if I divide on both sides with mass 1 by m dm by dt, because m is this one, so I can write on the right side I was having this value and I'm dividing with m. M is what? M naught e power t by tau. So you will have 1 by tau. So 1 by m dm by dt is 1 by tau. We can put g plus v by tau equal to acceleration. In my problem, I'm asked to give time of ascent as well as maximum height reached. So I have two choices for acceleration. I can choose acceleration as dv by dt, or I can choose something like v dv by dx. So if I go with dv by dt equal to minus g plus v by tau, we can rearrange the things. I think we can put dv by g tau plus v equal to dt by tau, taking integral on both sides. Initially velocity is u, finally velocity is v, in time interval sum 0 to t. We would arrive at minus ln gt plus v. Substituting the limits, I would have u to v, that is equal to t by tau. I'm asked to give the time of ascent. So anyway, first of all, I'll make that ln gt v by gt plus u. Gt plus u is nothing but you will get another gt. So that would be the expression. At maximum height, we can substitute v0 and t equal to time of ascent. We are asked to give time of ascent. So I would have what? If I put v0, so I would have minus ln g tau by 2 g tau equal to time of ascent by tau. Therefore, time of ascent I would have tau ln 2. That's the time of ascent. I am asked to also give the maximum height reached. Again, I am taking the same expression, that is minus of g times v by tau is acceleration. So I would have acceleration as v dv by dx. So let me rearrange the things. I would have g tau plus v by tau. Tau is a constant. So I would rearrange the things, minus dx by tau, and I would write v by dv by gt plus v. We can minus 1 by tau integral dx, and this would be written as I think I can write plus gt and minus gt. If I write a plus gt, I think I can write 1 minus g tau by g tau plus v. dv. I'll go with 0 to maximum height. On the right side, as I'm integrating over v, I should go with u to 0. So this is minus h by tau, which is h maximum. And if I take integral, yeah, v, so v means I'll have minus u upon substituting of the limits. Minus g tau is as it is. So ln g tau plus v. That would give me ln g tau by g tau plus u. So this would give me h by tau equal to u plus gt. But u is this one. So I would have ln 1 by 2 because u is gt in the problem. So again I have u gt. So h is equal to g tau square 1 minus ln 2. So that is maximum height reached.